Cameras on life support. All right. I'm kind of assuming there's no question, but are there any questions about anything before I get into? You guys are like, we don't know, dude. You still got our tests. I'm like, all right. Okay. What's that?
That's a question on you.
What's that?
The one you asked?
Oh, okay.
Yeah.
Okay, all right. So given and a couple of key facts we have to know going in. Let me start nice. Oh shit. None of you guys have any for pre-calc, I don't think. Nope. So I love teaching this in pre-calc because sine is a nice guy and cosine is an asshole. What do I mean by that? Cosine of a plus b is cosine says me first. Screw you. Me first. Me first. Oh, you got a plus. That's nice. I'm going to put a minus. And now it's your turn, sine. Dude, sine is a nice guy. He says, all right, I'll take a turn, and you take a turn. You got a plus. Okay, I'll keep it as a plus. And then I'll take this, and you'll take that. And yay, all right. All right, so that's just the way I remember it. I don't know how you guys are like, I have 0 ways to remember that. So I'll use your way. Okay, it's fine. Good. I like it. So if that was a minus, that would be a minus. If that was a minus, that would be a plus. All right, so we need one of those 4 facts up here. There are 4 facts up here. We need one of them. The other fact we need is something that the book discussed a bit that I didn't really discuss, which is what's the limit as x goes to 0 of sine x over x. I think it showed up in a couple homework problems. But nobody asked about it, so we didn't end up talking about it. They do it graphically. They do it by feeling it out. There's a geometric way to do this that I really don't feel like doing. But has anybody taken any physics? Some of you? Sometimes you'll have like a pendulum, and if you swing it by very small values of theta, you say sine theta is approximately equal to theta. So what this ends up being is, this limit ends up being what? And you could use, the geometric interpretation ends up using squeeze theorem. But we're not going to do all that. We're just going to go, if you graphed sine x over x in your calculator, you could trace it. You can see that it is approaching 1 from both directions. And what this really says is sine x and x, they both approach the same value at 0 at the same rate. Right? Exactly the same rate. That's why it comes out to be 1. So if you try it, put your calculator in radian modes if you want to play along. Do sine of 0.003. What do you get? Yeah, 0.00299. Would you say that is the same? It's about the same as that, right? So sine of this is approximately equal to that for very small values of x. Very small values of 0. I like that. Okay, that's plenty. All right. So this is a fact. This is a fact that we now know. The book talked about it.
Where's like a small number cutoff? Like less than 1?
No, there is no small number cutoff. We are going to talk about like error tolerance kind of stuff. So it all depends on how good you want this approximation to be. What is your own personal error tolerance? So we will do what's called linear approximation. So sine x is approximately equal to x for small values of x. And so your question is, well, what's small mean? And then my response would be, you tell me. I mean, so it all depends on your error tolerance. So we will discuss, if you have an error tolerance, how far off you accept to be, then you can determine an interval for x around 0.
Yeah, we talked about the epsilon. It's kind of,
Thankfully, it's not going to be epsilon delta.
and that's similar.
Because I say that because I know how you all feel about it. But you can see it's sort of related. Okay, so I have these facts, I have that fact. How do I just start to attack this question then? I mean, how do I always find this before chapter 3? Yeah, so the limit as h goes to 0 of
F of x minus h.
Minus f of x over h.
you know, minus there would actually be the same thing, to be honest, but we just chose to go that way, so there you go. So this is what you guys had to do on the test in a few places.
Yeah.
And the idea is very simple, right? I always have to have 2 points. I want the slope at x, so I always calculate it from x to this point here. And then I just make that point get infinitely close. It's always 2 points, but it gets so damn close it's basically 1 point. That's the idea behind slope at a point of a curve, right? Okay, good lord, I can never read you guys at all. Alright. So I just plug and chug. So what do I put in here? So, what's that? So now you see why I need a fact from over here. So how can I rewrite sine of x plus h? Good. Sine's a nice guy. We'll take turns. You got a plus in there. I'll be a plus, sure. I'll do the h now. And cosine's like, yeah, that's right. Minus. Turns out cosine's an asshole in a few different places, so it's kind of good to remember. Is that cool? Now watch this. Everything in here is continuous on its domain, correct? Not just because I just said so, but because you know it's true. Right? So I can pull, what's the limit as h goes to 0 of cosine h? This is not cosh, by the way, if you know hyperbolic. I don't know if anybody does. Yeah, as h goes to 0, cosine it's 1. So that goes to 1. Is that cool? And what's sine x minus sine x?
Well, there's multiplication there.
Say again?
Sine x times cosine.
Beautiful. So sine times 1 is sine.
Oh, okay.
Sine minus sine is gone.
Okay.
I like it. Keep me honest. You guys with me so far? Does everything I just did make sense?
Yeah.
Cosine of 0 is 1, so the limit is 1. It's continuous through 0, so it's no problem. So sine minus sine is 0. So now look, what's the limit of sine h over h? 1. So what do I get then? What do I get left? What's left? That's 1. Cosine x there. So the derivative of sine x is cosine x. That's neat. If you think about it, sine looks like this. Right? In a horrible way, but oh well. What's the slope here? 0. What's the slope here, maybe? Maybe it looks like it could be 1, right? What's the slope here? 0. I mean, what am I drawing? Cosine, isn't it? So, I mean, is that a proof? No, that's the proof. But that is kind of like after the proof going, oh yeah, I could have maybe seen that before. That makes sense. And that's doing the thing that wasn't on this test because it's going to be in the next test, and that is tracing f prime given f, right? I didn't put that on there, so I'm going to put that on the next one. All right, how are we doing so far? Is that cool? Yes, sir.
What happened to the 1? Like the 1 and then a plus another 1.
No. So this is sine times this, and this went to 1.
Right.
So it's sine times 1 is sine, minus sine is gone.
Oh.
This is sine h over h times cosine.
Right.
That went to 1, so I'm left with cosine. The 1s are all attached to other things, so I don't write them. I like it. Yes?
I see you got that sine x over x with that formula, and does that work because h is going to 0? But it's
Anything in that form. Yeah, what is x? Some arbitrary letter that somebody way back in time decided to be the variable, right? So what if it's h? It's the same form.
So if we made sine of h, if it was just plugged in a 0, that wouldn't have worked for h.
How do you mean? Sorry.
We can't.
Yeah, you can't plug a 0 in because sine of 0 is
Sine of 0 is 0.
0, and h would go to 0. So 0 is 0 indeterminate.
Okay.
That's why there's a ton of different ways to prove this statement.
But when you got to that line, like you kind of got to pick which ones you wanted to go to 0.
No, I didn't. What's got to go to 0 is h. So, all right. Is everybody cool? Everybody's cool with these going away, right? Because the cosine goes to 1. The cosine of 0 is 1. All right, so then I'm left with this. Right?
See, I see that I thought when you replaced the h's, you replaced them all at the same time.
Totally.
Yeah, so you said like the cosine of 0 is 1, but you're saying the sine of h is something. Like as soon as
No.
I
All right.
replaced that
All
first
right,
one,
all right.
I replaced all of them at the same time.
Do it. I'm sorry.
When I replaced the h, I try to replace them all at the same time.
Well, don't. That's crazy. So what I'm saying is, I can bring this in because everything's continuous, right?
Yeah.
And this is determinant. This piece is determinant, so I can do the limit of it.
Okay.
Not a problem. And it's because of those laws, all those laws in that one section about how we can distribute a limit across addition, right? You can bring it through. Just bring it into a continuous function. All of that is so that I can do this kind of thing. I can evaluate the limit of this term because I can bring the limit to it.
Okay. I see how you did it. I would have made the sign of h also. I would have made it 0. When I did the first part, I would have done it to the second part too. I don't understand how you did one side but not the other side. I see how you set the limit on the left. I see how you can do the limit of all of them, right? But how did you just do one side and not sine of h? Why did you not replace that with 0?
Well then it would have, at the end, it would have been 0 over 0.
Yeah.
Right?
Yeah. Which would have been.
But this part, so all right.
So it doesn't actually get to 0, right? Like, where it's gonna go.
But the other side did, right?
Alright, so if I bring this into each piece. Actually, let me let's see. All right.
As like you said before, you can actually find out what the limit of cosine of h is as h approaches 0. Right? You know it's 0. Right? It's something that you know, if you've proven it already.
All right.
The one you can't find out.
Yes, ma'am.
What section is that? Or is it from the test?
That's from the test.
From the test.
From the test. So this piece, this is sin x, right?
Yeah.
Okay, sin x minus sin x is gone. This would be 0 if I plugged it in, and this would be 0 if I plugged it in, so it's indeterminate.
Okay.
So then to do that, I pull that back out, and so I can analyze this. They both go to 0, therefore between the two of them, they should work together to agree on
I
something.
see what you're doing now. When you split the limit up, it makes it a little different.
All right, I'm
It makes it a
sorry.
little different.
So I kind of did that quickly, but I'm using the limit laws, and then if you do try to plug a 0 in here, you do get 0, I agree, but then you get 0 down here also. So overall, it's indeterminate. So then you take a step back and you say, let me analyze them together. Because when something's indeterminate, what do you hope is going to happen with the top and the bottom? Somehow, the problem's going to cancel. Trig functions are not as nice as polynomials, though. Polynomials, you'll always be able to factor them or something, right? Trig function, oh shit, you need this weird-ass thing here that you could prove it geometrically. You can look it up. You can look what the book says. You can trace it on your calculator. You can see that it looks like it's going to 1, and so forth. But now that I know that's true, I can then just apply it to anything. So real quick, if I had the limit, just to make sure this other point that you were bringing up, as x goes to a of sine of x minus a over x minus a, what would that be? 1. It's the same form as that, right? It's shifted by a, so who cares? It's still going to go to 1. So anything in that form, the limit will be 1. I like it.
It has to be 1. We couldn't also have chose to make it like indeterminate also.
No. It's not a choice we're making. It is 1.
Okay.
It is. This is indeterminate, but it does become 1.
Okay.
Yeah. Okay. To be completely honest, I mean, if I really felt it would help us, I could remember the whole geometric argument where you just construct these triangles that represent trig, and you create inequalities that you can then use the squeeze theorem
I'll go
on.
with
That's how you prove it. I
agree.
just really didn't want to do that.
It's cool.
Right? I just yeah. Okay. Thank you. Okay. No. All right. So that's the first little thing, and I just wanted to do it because it was on the test, and I thought it'd be a nice little example of we do so many polynomials with this that it's easy to not realize it still has to work for any function at all that's differentiable, and this has to somehow work. But any more difficult function that's not a polynomial, you're going to run into weird shit like this. That becomes their own little problems that you have to solve. Polynomials are awesome. They kick ass in this form. Almost any other function gets really freaky. Radicals are okay. We just got to do conjugates, right? Fractions are okay. Oh shit, hopefully they are, because they asked you a fraction question, like f of x equals 2 over x or something. You just had to get like denominators and put them together. You would have been fine, right? So those kind of things I can algebraically figure out how to manipulate them. Trig functions get freaky as hell, right? Trying to figure out derivative of